Now that we properly filled out all the missing values, we can continue and convert the dollar amounts to euros. As we explained in the first part of the practical example, we are based in the European office, so we must keep all records in euros as well as dollars. To do this, we need the exchange rate between the two currencies at the time of each loan application. As we saw last time, the issue dates were just months rather than specific dates. Lucky for us, the EUR-USD CSV contains the average monthly exchange rates for 2015. Let's take advantage of that. In a new cell, we'll create a variable called EUR_USD and set it equal to np.generateFromText. In the parentheses, we'll add the name of the CSV file we just mentioned, followed by a comma delimiter and an autostrip argument set to true. As always, we also call the variable on the next line and run the cell. We see an array with NANs across the first row. These are probably the names of the columns, so let's improve the data import by setting the data type to strings and see what each column represents. In the top row, we no longer see missing values, but rather the following column names: open, high, low, close, and volume. They all represent data about stock prices and exchange rates we typically keep track of. The first four express the four most important characteristics of the exchange rate for a given day. The exchange rate at the beginning of the trading day, the daily highest, daily lowest, and the exchange rate at the end of the trading day, in that order. It's important to note that even though the fourth column reads close, we're actually using the adjusted closing prices instead. The last one represents the number of trades that have happened during the given trading day. Of course, that one is full of zeros in our case, because we can't really buy or sell the exchange rate itself. In analysis, we often prefer to use the adjusted closing price, which we'll find in the fourth column. Since we only care about the numbers from that column, we can revert the D type to the default, skip the header, and set the use columns argument to 3. That way, we'll only import the exchange rates we need, without keeping track of high, low, or other characteristics for the monthly values. Superb! We're not using a constant exchange rate, so we'll create a new column to store the exchange rates for each account. We'll start by setting exchange rate equal to the first column of the string dataset, because it contains all the issue dates. But before we do so, here's a reminder what this looks like. The value represents which month the loan was issued, the 1 corresponding to January, 2 to February, and so on. The 0 represents all accounts where the date wasn't provided. Then we'll create a for loop that goes through the range from 1 to 13, one iteration for every month of the year because the upper limit 13 is not included. Inside the loop, we'll set the exchange rate variable equal to np where. The function will substitute the 1 for January with the average exchange rate over that period. Then it will move on to February, March, and so on until accounts for all 12 months are assigned an exchange rate. We use I-1 here because indexing in Python starts from 0. So even though January is represented by 1, the index for EUR_USD must be 0. Okay, but what about accounts with no issue dates? Well, the more reasonable solution is to assign the annual exchange rate for 2015. So we once again set exchange rate equal to np where. The condition is for the variable to equal 0 because that's what we assign to missing elements for the issue date column. The substitute value will be the annual exchange rate, which we assume to equal the mean of all exchange rates for 2015. We can find it with the help of npmean. Then, if the condition isn't met, the value remains the same. Right. On the last line, we'll display the new variable. We see that it now contains the associated exchange rate for every element of the dataset. After we store this information into an array, we need to add it to the dataset. To do that, we need to know if the new variable and load data numeric have compatible shapes. That's why we call the shape attributes of both. We see exchange rate is one-dimensional, while the numeric dataset is two-dimensional. Therefore, we must reshape the new array, right? In a new cell, we set exchange rate equal to np reshape. Add the variable as an input, and set the shape to 10,000 by 1. Now, we can horizontally add the new array to the end of the dataset, as both are two-dimensional. How do we do that? We call the hstack function and add loan data numeric and exchange rate as the inputs. Now, the last column of the output matrix contains all the exchange rates, and this matches our expectations. So, let's set the dataset variable equal to this output. Run the cell and move ahead. Of course, since we added a column to the array, it's only fair to also include it in the header. To do that, we'll set header numeric equal to np concatenate and add header numeric and the words exchange rate in quotation marks. If we try to run the cell now, we'll get an error message because the header variable is a one-dimensional vector, while the text in quotation marks is a zero-dimensional scalar. The easiest way around this issue is to turn the text into an array with the help of the npArray function and adding square brackets on each side. To stick to good practice, let's display the variable we just created. We see a new header, which contains exchange rate at the back, so we've successfully added a column to the dataset. Excellent! In the next lesson, we'll continue the topic of currency exchange. Can't wait! Until next time!